There we go. Okay, so again, I had you guys graph each pair of equations into the same window and just kind of pay attention to what's happening. In A, basically, what were those two functions?
Lines.
They're both lines, okay. And what did you notice?
They intersected -1, -1.
Okay, they had an intersecting point. Anybody notice anything else?
It was like
They had
reflected
like
over y equals x.
X and Y.
Okay, reflected over x equals
Oh
y.
my god.
Exactly.
That's
All right, which means same thing happened in B,
Yeah.
right? And you'll notice like the images are similar to one another, but not alike, right? And then in C, what was different about C and D? Several of you were asking about, and when you're graphing in the Desmos, you had to put in domain restrictions, right? Okay. And let's think about Y. Think about the g of x in both C and D. If you didn't have a domain restriction, what would the graph look like? A parabola. Exactly. Okay. But the original function, did that look like a parabola? No, what did it look like? Curve, or maybe half a parabola? Okay. All right. So those are the things I kind of wanted you to pay attention to. The fact that it's a mirror image. So like you said, it's a mirror image over y equals x. I'll write that down. Mirror image over y equals x. Did anybody pay attention to the coordinates and how they changed?
X and Y was switched.
Yes, that's the next thing. So a function f is a set of ordered pairs x, y, right? If it has an inverse function, it means that the inverse will have the opposite coordinates, right? So instead of x, y, the inverse will have y, x. So our notation for inverse function is this f to the -1 of x, right? And we pronounce it as f inverse of x. Inverse of x. Or inverse of f of x. Okay. And again, you don't want to confuse it with, say, like 3 to the -1, right? They're not the same. 3 to the -1 is equal to 1/3. It's not the same thing. This is an inverse of x. So we won't, not the same. So in our first example here, all we have is a graph, basically just made up of piecewise linear functions here. And we're just going to sketch the inverse based upon the information that we know. Right? So I'm just going to sort of look at the original graph, and I see here that I have this point at -4, 1. And so if I flip those, it becomes 1, -4. 1, -4 down here. All right. I also have this point here, which is at 0, 5. Again, if I flip those, that's going to take it to 5, 0. And I have another coordinate here at 2, 5.5. And so the opposite of that will be 5.52. And the final one here is at 4, 7. And so that'll go to 7, 4. And I didn't scale my graph out far enough. So we'll just kind of estimate it to be about there. All right. And in the end, I'm going to connect all of it. And there is our inverse function. And again, it's mirrored over the line y equals x. And so when y equals x, all right, 0, 0. I know, it's Monday. So this is our line y equals x, our line of reflection. So again, it's like taking the graph and cutting, or not cutting it, but folding it in half diagonally from corner to corner, from the upper right corner to the lower left corner, and then we get a mirror image across it. All right, any questions on anything so far? Okay. So sometimes we are asked to find the equation of the inverse of a function. So we'll start with just this very basic linear. So let's say I'm given f of x is equal to 2x plus 7. So the first thing we're going to do is replace the f of x with y. So this will now be y is equal to 2x plus 7. And then as we saw earlier in an inverse function, it's the x's and the y's that switch places. And so that's what we do in the equation. I'm going to change this y into an x. And any x that I see is now going to become a y. And then from there, we're going to isolate the y. So subtracting 7 from both sides, I get x minus 7 is equal to 2y. And then divide both sides by 2. So now I have y isolated as y is equal to x minus 7 over 2. And then the very last thing would be to go back and replace the y with our inverse notation. So we would have f inverse of x is equal to x minus 7 over 2. And that's the inverse. Okay, any questions on that? All right, so A and B are very similar to what I just walked through, so I'm going to go ahead and let you guys work those two on your own. Okay, so there's A and B. How'd we do on those? And I know some of you separated the x plus 5 over 3 into x over 3 plus 5 over thirds, and that is perfectly acceptable as well. All right. Scooch that over. Okay, our last one here, f of x equals negative x cubed plus 3. So same process. We'll change f of x into y. Negative x cubed plus 3. Switch the x's and y's, so x equals negative y cubed plus 3. I know that I need to get y by itself, and I don't want to work with negative y, so I'm going to add y cubed to both sides, and I'm going to subtract the x from the other side. So I'll get 3 minus x there. All right. And again, we need y to the first. Right now it's y to the cubed. How do we undo a cube? Cube root. Bless you. So I'll take the cube root of both sides, and we end up with y is equal to the cube root of 3 minus x. And then the final thing, again, switch to our inverse notation. So f inverse of x is equal to cube root of 3 minus x. Any questions on what we've done so far? All right. So this next part here, it's asking us to graph each function and its reflection over the line y equals x, and then asking us, is the reflection a function? All right. So for our first one, where we've got 3x minus 1. What is 3x minus 1 the graph of? What kind of function is that? Linear, right? So this is just a linear function. What's my y-intercept? -1, and my slope is 3. All right, so there's my intercept, and then 1, 2, 3 over 1, 2, 3 over 1. Okay. So there's the graph of the function. I'm going to try to use a ruler on here because my lines never come out very straight on the screen. Oh, that helped a little bit. Okay, so this is f of x. Okay, so now that we've got the function in, again, we can do the graph by doing what? Switching the x's and y's. Okay, so right now I have 0, -1. So I can switch that to -1, 0. All right, and we'll go ahead and get one more point in here to get our line in here. This is 2, 5. So that's going to flip to 5, 2. All right, and go ahead and connect that. So again, here is our inverse function. And the question is the reflection the graph of a function? Would we classify that inverse as a function?
Yeah.
Yes. And how do we know that? Vertical line test. Yes. So f inverse of x passes the vertical line test. Therefore, it is a function. All right, so if we move to B, where I've got f of x equals x squared, what is that the graph of? What's x squared? A parabola. There we go. So let me just get a couple points in here. All right, so I'm going to mark some of these. We got a vertex at 0, 0. We have a point here at negative 1, 1. We have a point here at negative 2, 4. We have a point here at 2, 4, and a point here at 1, 1. All right, so if I go in now and do the inverse, I'm going to get 0, 0, 1, 1, 1, negative 1. I'm going to get 4, 2, and also 4, negative 2. And so again, this one is the inverse function, and this one is the original. So now that we've got the inverse, or the reflection, can we say that it is a function? No, and why not?
It doesn't have vertical
Yeah,
line.
does not. So this does not pass. So, question to you is, could we have determined that without graphing the inverse or the reflection? Yes. What could we use?
Well, because you switch the XY, you do the horizontal.
Exactly. Right? Exactly. If we're talking about graphically, if the function f of x passes the horizontal line test, and again, that's when the graph intersects the horizontal line only once. So again, if the function passes the horizontal line test, then we know the function itself will be the inverse will be a function. So, quick way to check. All right, so this kind of brings me back to in the exploration. Remember, we had two that had square roots that were involved, and the inverse of them had a domain restriction, right? So that's where this would come into play. So let's say that we were doing f of x equals x squared. However, we were going to restrict this to x greater than or equal to 0. So when that happens, that means the only part of the function that would be graphed is the right side and by restricting the domain, would that now pass the horizontal line test?
Yes.
Yes. Okay. So that's what you kind of want to pay attention to when you're working with those even roots, right? And even exponents. Do we have a domain restriction that would allow the inverse to be a function or not? Okay. All right. So in these, consider the given functions, determine whether the inverse of f is a function. If it is, then find the inverse. So let's see, quick review. What's happening in A? What's our parent function? x cubed. And then what's happening to our x cubed?
It's
Stretched by 3, and then vertical shift down 2. Exactly. So, do we already have the image in our mind? Yes. Sorry, this is not going to come out very straight. So again, what do we know about cubes? What's the end behavior?
Oh, it's like the
Yes.
the opposite.
Yeah. The right side will go where? Up or down? Right side's going to go up. The left side's going to go down. Again, we just said that it's going to shift down by 2. So we know this, and we know we have a stretch of 3. So that puts it about there and about here. So we're going to end up with this curvy thing. Sorry, this did not look very curvy, but trying to get that in there. Right, so again, use the information you already know. We've done transformations. We've done them on cubes, so we know what it looks like. So can we tell? Is the inverse going to be a function? Yes, and that's because this passes the, is it the vertical line test? Horizontal line test, yes. So f of x passes the horizontal line test. All right. Therefore, f inverse of x is a function. All right, so it asked us if it is a function to go ahead and find the inverse. All right, so again, we're going to switch the x's and the y's. So this is going to become an x equals 3y cubed minus 2, and then solve for y. So we get an x plus 2 equals 3y cubed. Divide both sides by 3, and then what would be left over from there?
X plus 2 equals y cubed.
Okay, and then we need y by itself.
Cube rooted.
Take the cube root of both sides. Cube root, and so in the end, we have an inverse of f is equal to the cube root of x plus 2 over 3. Yes?
So when they say find the inverse, do they mean actually graph or just find the equation for it?
Just find the equation of it, yeah. All right, so let's talk about b. We've got negative 2x squared plus 5. What do we know about that graph? It's a parabola. Stretched by 2. What does that negative indicate?
Oh, reflection.
It's going to reflection. So what direction will this parabola open? Opens downward. And then the final thing is it goes up by 5. So without sketching it, we already know that it's doing something like this. And if it's doing something like that, will its inverse be a function? No, it will not. Okay. So f of x does not pass the horizontal line test. Question? Yeah. So f inverse of x is not a function. Right. And if it's not a function, we're not going to solve for it. All right. I'll give you guys a minute to discuss with your table mates the next one. What's going on with f of x equals x to the 4th minus 1?
Well, is it also
Oh, yeah. Because remember the odd ones go like that.
Yeah.
Even ones like that.
Yeah.
Oh, yeah. The even ones are always the same direction.
So what did we discuss? What's going on with an x to the fourth? Okay, and behaviors in the same direction. This has two tails going where? Two tails going up, so it will not pass. So again, we know it does this. So f of x does not pass the horizontal line test. So f inverse of x is not a function. Okay. So who of you thought all those rules we learned about graphs would just go away? Yeah, just keeps coming back and keeps coming back. Okay. Okay. Now this next part is a little more algebraic. So here it asks us to verify that two functions are inverses. Okay. And so if you're asked to verify whether or not functions are inverses, we do this. F of g of x equals x and g of f of x equals x. Otherwise known as, what are these functions called?
I don't know what they're called.
Who remembers, huh? Starts with a C? Not congruent. Huh? No, not complex. Not conjugates.
Complex.
Not complex. Compo. Composition.
Oh gosh, how could we forget?
Why did that take us?
Yeah. I was so set on it being complex. I was like, sure, that was it.
Yeah, these are composite functions, all right? So we're going to plug G into F and solve, and we're plugging F into G and solve. And notice that the and is bolded. It has to happen in both directions. All right. So in this example, we want to verify that f of x equals 2 over 5x plus 1 and g of x equals 5x minus 5 over 2 are inverse functions. So again, we are going to build this composite function here. So for f, I'm going to plug in g, and g is 5x minus 5 over 2. And just a reminder, that notation is telling us that wherever we see x in f, we're going to replace x with 5x minus 5 over 2. So in f, where we have 2 over 5, x is being replaced with 5x minus 5 over 2 plus 1. Okay, so at first glance, does it look like a terrible thing to have to solve? Yes, but what do you notice? The 2's are going to divide out, that goes away, and then what happens? The 5's are going to divide into both terms, leaving us with x minus 1 plus 1, and that's just x. Okay. So it worked in that direction, but again, in order to verify, we have to check the other direction as well. So on the other side, I've got g of, and my f is 2/5 x plus 1. And again, I'm going to plug that in for my x's in g. So 5 here, and replace x with 2/5 x plus 1 minus 5 all over 2. Again, at first glance, does it look horrible? It does, but does it clean up pretty nicely?
Yes.
Yeah. Right. If I multiply this 5 over here, what happens? Over 5 though, which means we're left with 2x. And distributing the 5 over here gives us plus 5. We have a minus 5 on the outside here over 2. And what just happened? That's gone. 2x over 2 is x. Oops, not 2. Is x. Okay. And then we can say, since f of g of x equals x, and g of f of x equals x, f of x and g of x are inverse functions. Alrighty. Any questions on what we've done? Alrighty. I've got 2 for you guys to try. Oh, there we go. Okay. So A, hopefully you found that it worked in both directions. And then in B, it froze again. It did not. Okay, so in B, if you find in one direction you don't get X, do you have to check the other direction? No. Once you find one that doesn't work, the only thing I would be careful of is double check your arithmetic. Make sure you didn't make an arithmetic mistake, right? Okay. So again, once you find that one doesn't work, then we can say that they are not inverses and we won't continue. Okay. Questions on these? Okay. So the next part, everybody's favorite. All right. Yes, we love application problems. Okay, so when calibrating a spring scale, you need to know how far the spring stretches based on given weights. Hooke's law, I understand you guys have not gotten to that in physics yet. Okay, so Hooke's law states that the length of a spring, or that it stretches, is proportional to the weight attached to the spring. So a model for one scale is L equals 0.5 W plus 3, where L is the total length in inches of the spring, and W is the weight in pounds of the object. Okay, so the way this equation is given to us, what is it it's set up to solve for? L, which is the length, right? So this is for finding length based on weight. Okay. All right. But what if you had the length and you wanted to know what the weight is? Okay. Yes, you can plug in and solve, but if you had a whole bunch of them, it's much easier to just go ahead and isolate the W. So when you're working on application problems and it asks you to find the inverse model for the scale, we're not going to change the variables. Okay. You leave the variables as they are, and all you're going to do is solve for the opposite variable. Right. So right now, again, this is length in terms of weight. We're going to find weight in terms of length. So again, I'm not going to switch my variables around. I'm just going to isolate the W. So again, if we're starting with length is equal to 0.5w plus 3, and we're solving for w, that means subtracting the 3 from both sides. That gives me 0.5w. That's 1/2, so if I multiply both sides by 2, that's going to give me w is equal to 2L minus 6. Okay. Again, I'm not switching any variables or trading them. So now what we can find is what is the weight in terms of the length. So in B, when it says, if you place a melon on the scale and the spring stretches to a total length of 5.5 inches, how much does the melon weigh? Right? Our equation is already set up to solve for the weight in terms of length, and so it's going to be much easier just to plug in. Right? So again, if the weight is equal to 2 times, the length here is 5.5 minus 6. That's going to give us 11 minus 6. Therefore, how much does the melon weigh? 5 pounds. Okay. Yes, Jocelyn.
So for D, you wouldn't be able to use like the original model.
You could, right? So if we didn't solve for W, what we would have is we would just have this 5.5 plugged in here, 0.5W plus 3. Would we still end up getting the same?
Yeah.
Yeah. Okay. Again, it's just a little more work. It's much nicer when you have the variable that you're after is already isolated, and then you don't have to keep undoing all of the arithmetic functions there. Okay, any questions on these? Okay. All right, so the last part, and we're just going to touch on this very, very briefly. This is just kind of an introduction to our exponential functions, and we'll get more into them next time. Okay. Or I guess after the test, so that's in a few classes. Exponential functions, what's happening here is we've got this form, y equals ab to the x power. Okay. And again, when we are graphing, usually we plug in our values of x and we find y to figure out what the graph looks like, right? So same thing here, except x is in the exponent position. Right? And we're going to have it on some base of b, and then the a in the front, that's sort of like the stretch or shrink, just like we've done before. Okay. So based upon what those values are, it's going to determine sort of the overall picture of what the graph looks like. Okay. And don't feel like you need to get all of this down. We'll just kind of discuss it, and like I said, we're going to come back to it. Right, so in our first one, as x is, if we just look at the blue one, as x gets large, what is y doing?
Decreasing.
Over here? Where's y going? On the blue one. It's increasing, and it's increasing pretty rapidly, right? So that one's like an exponential growth. Okay. Versus on the left side, if we look at the blue one, what happens as x gets larger? Yeah, exponential decay. All right, so we've got our growth and decay. What's happening with the red image on both of them? Okay, but they are, what's the relationship with the blue one? Reflections. They're just reflections over the x-axis. All right, and if you'll notice here, a is now less than 0 on both of them. Okay, meaning there's a negative in front. Okay, so do the rules change from the other reflections that we learned before? No, those don't change. Okay, I think when you have just letters in there, it makes it a little more difficult to understand. So I made some graphs here with actual numbers in. Right, so in all of these, a is 1, or in this case in the reflection, -1, and I just used a base of 2. Okay. And so you see in the red one here, if we have 2 to the x power, yeah, anything raised to the 0 power is always what? Always 1. Okay. And then again, we're only multiplying 1. So again, there's our first, our y-intercept there. And then again, we're exponentially growing because our base is larger than 1. So it's going to increase. Versus the one on the right-hand side, our base is less than 1. So it's between 0 and 1, meaning now we're shrinking. So if you think about this, it's the same thing. 1/2 to the 0 power is still 1. But what happens when I take 1/2 and I square it? It becomes what? 1/4, which is smaller. Okay, and so that's the shrinking aspect of this one. And again, the blue graph underneath is just a reflection over the x-axis, and that's indicated by that. We see the negative sign in the front of them. Okay. So again, we'll do more of these when we get further into this unit. So this is just sort of a little intro. Okay, are there any questions on what we've done today? Good. Okay.